In this video, we're going to start talking about concentration of solutions, specifically molarity. And before we can start talking about the concentration of solutions, I do want to define a solution. So a solution is a type of homogeneous mixture. If you remember when we were doing classifications of matter, right, we had pure substances under which we had elements and compounds, and then we had mixtures. And then under mixtures, we had two types, homogeneous or heterogeneous. And the difference between the two is essentially, does it look like a mixture or does it not look like a mixture, right? Heterogeneous ones, you can tell that there's different things mixed together by looking at it. So we said it was non-uniform in composition. A homogeneous mixture, when you first look at it, doesn't really look like a mixture, right? We said it had a uniform composition. So a solution is a type of homogeneous mixture. And there are other types of homogeneous mixtures. This is just the only one we're going to talk about now. So it's a type of homogeneous mixture. And essentially what makes a solution is that the size of the particles in it are pretty small. Other types of homogeneous mixtures will have larger particles. We generally classify them by particle size. Another defining characteristic of a solution is that if you let it sit for a while, those particles are not going to fall out of solution. So Kool-Aid was my example for a homogeneous mixture, and it is also a solution. If I mix up some Kool-Aid and put it in the fridge and let it sit there for a week, I'm not going to come back and find a pile of sugar and Kool-Aid powder at the bottom. It's going to stay in solution. So that's one of the things that defines a solution. So small particles, and they stay in solution if you let them sit around for a while. So a type of homogeneous mixture. There's two parts that make up a solution, our solute and then our solvent. And if you were to take three things and mix it together, like our Kool-Aid example, right? We have water, we have Kool-Aid powder, and we have sugar, then two of those things are going to be solutes and one is going to be a solvent. You're only ever going to have one solvent in a solution. You can have more than one solute. So if I was to take 10 things and mix it together, and I can't tell that things are mixed together, right? It's a homogeneous mixture. And if I let it sit around for a while, nothing's going to fall out of solution. Then 9 of those things are solutes. Only one of them is a solvent. And the solvent is going to be the component that's present in the larger amount. My solute or solutes are going to be the component or components that are present in the smaller amounts. So in our Kool-Aid example, the Kool-Aid powder and the sugar are both solutes. My water is my solvent. So if I was to take solute plus solvent, I get my solution. So again, the solution is the total, right? It's made up of two components, the solute, the solvent. We can have more than one solute, only ever one solvent. Solvent is present in the larger amount. My solute is the component present in the smaller amount. It is really common, watch out for this, to assume that if water is part of our solution, that water is the solvent. That's not always going to be the case. So an example, if I had a 70% methanol solution, and this is an aqueous solution. So what this means for us is that 70% of it is methanol. Methanol is just a type of alcohol. And then 30% of it, right, because it has to add up to 100, is going to be water. So in this example, water is actually my solute, right? I have less of it. Only 30% is water. Methanol is my solvent because I have more of it, right? The solvent is the one that's present in the larger amount. The solute is the one that's present in the smaller amount. So in this case, water is actually my solute. methanol is actually my solvent. If I was to have a 30% methanol solution, then those two things are going to be reversed, right? Again, it's in water, and I would have to tell you that. So 30% of it is methanol, 70% of it is water. And now if I was to identify the solute and the solvent, they're going to be different than they were before, right? This time, the one that I have less of, my solute, is my methanol, and the one that I have more of, my solvent, is water. So do watch out for that. If you have a solid dissolved in a liquid and that liquid is water, then water is almost always going to be the solvent, right? If I was to take a smaller amount of water than I have sugar, right, I'm not going to be able to dissolve it. Here, methanol is a liquid, water is a liquid, so it doesn't matter which is which, it's just the proportion. So do be careful. Water is a very common solvent, but water can also be a solute. It doesn't have to be a solvent every time we have water. So watch out for things like that. The other thing I want to say about solutions before we start talking about units of concentration is that solutions can form between any states of matter. So in my Kool-Aid example, it was between a solid and a liquid. In my methanol examples, it was between two liquids. We could have two solids, so something like brass. Brass would be a homogeneous mixture between two different types of solid metals. We could do like soda water or pop soda, right? It's carbon dioxide, which is a gas in water. So gas in water. You can make, like I said, solutions between any of the states of matter. So concentration. When we're talking about concentration, we're actually talking about how much solute is there per solvent or solution. So we're actually talking about a number. So when I say what is the concentration, we want a numerical value to tell us how much solute per solvent or solution we have. So this tells us the amount of solutes per solution or solvent. So something that's more concentrated is going to have more solute. Something that is less concentrated is going to have less solute. I am saying solution or solvent. It depends what unit of concentration we're talking about. All the ones that we're going to do in this chapter are actually going to be per solution. Chapter 11 is also on solutions, and in that chapter we're going to actually have one that's per solvent. So whether it's solute per solution or solute per solvent, it depends what unit of concentration we're talking about. The main focus of this video is going to be molarity. So molarity is a unit of concentration. It tells us the amount of solute per solution. Its abbreviation is a capital M. Please make sure it's capital. A lowercase m is actually our abbreviation for molality, which tells us solute per solvent. It's a different type of solution. So please make sure that your capital M's look like capital M's. And molarity tells us the number of moles of solute per liter of solution. So that's how we're going to define molarity. So moles of solute per liter of solution. So an example for us, just solving for our concentration. So what is the molarity of a solution that is prepared by adding 32.46 grams of sodium chloride to a total volume, say a total solution volume of 500.0 milliliters. So we're making a solution. We're taking 32.46 grams of sodium chloride. We are dissolving it into a total volume of 500 milliliters. Do be careful on this wording. If I said we added 500 milliliters of water, then that 500 milliliters is my solvent, right? Not my solution. Solution, if we go back up, way up here, solution is my total, right? It's both of these things added together. So if I just said 500 milliliters of water, that's this number, not this number. So do be careful. We can do one like that after, but right now I'm saying the total solution volume is 500 milliliters. So that is the solution volume. I know that molarity is moles of solute per liter of solution. We have grams, so we're going to have to convert from moles to grams. And then it's liters, I have milliliters, so we'll need to convert from milliliters to liters also. So how do we convert between grams and moles? In the last video, I said we're never going to do it differently than this one particular way. Yeah, good. Hopefully you said molar mass, right? Every time we have grams of our substance and we need moles of our substance or vice versa, we're always going to use molar mass. So I'm going to take 32.46 grams of sodium chloride. Because grams are on top, I'm going to have to divide by my molar mass to make them cancel. So we're going to grab the periodic table in our calculator, and I'm just going to add them together without writing down the work. I hope at this point you guys are pretty comfortable calculating molar masses. If you do have questions, please make sure to ask. So there's one sodium, there's one chlorine. So I'm grabbing my numbers off the periodic table for sodium and the one for chlorine. And when I add those together, I get 58.44 grams per mole. Again, that has to go on the bottom so my grams cancel. So taking 32.46, dividing it by my molar mass, I get 0.555, one more digit, 4 moles of sodium chloride. So that's my moles of solute, right? That's the number that's going to go on the top here. I still need liters of solution. I know that I have 500 milliliters. I know that there's 10 to the third milliliters, or 1,000 in 1 liter. Right? We need to divide. And if you can do this in your head just by moving your decimal point over, by all means do that way. That's how I would do it. I would just take this, and I know that when I divide by 1,000, I'm going to move my decimal place 3 places. So 1, 2, 3. So it comes out to 0.5000 liters. Be careful not to drop any of your significant digits, right? This here is 4 significant digits. That decimal point makes all of those zeros significant. 1,000 milliliters in a liter is exact, so that's infinity. 4 is less than infinity, so I want 4 in my answer, and that would be 4 significant digits. So be careful. Don't write 0.5. You're going to lose points for that. And if it's a multiple choice problem, like on our Canvas quizzes, you don't get partial credit for multiple choice, so please be careful. Pay attention to your significant digits when you're doing that. So that's my number that goes on the bottom, right? That's my liters of solution. So now we just have to divide those. So 0.5554 moles over 0.5000 liters. And I'm just punching this into my calculator right now. And I got 1.111. It actually comes up in my calculator to be 1.1108. But when I round to 4 significant digits, that 8 is going to round that 0 up to a 1. For units, you have a couple options. You can write the capital M for molarity, or if you wanted, you could write moles per liter. And I use both depending on what I'm going to do with that number. Something like this where I'm just solving for molarity, I'm generally going to write the capital M for molarity. If I'm using this number for something else, I'll tend to write it out. And I'll show you what I'm talking about here in another example. How we would read this, it's kind of weird. So the first one where I have the check mark with the capital M, I would say you can do it two different ways. I could say my molarity is 1.111, or I could say it's a 1.111 molar, M-O-L-A-R, solution. So if you're using the capital M as an abbreviation, it's molarity. If you're using the capital M as a unit, then you would read it as molar. So it's a 1.111 molar solution, or 1.11 moles per liter. Either one works, but that's how you would read that. So 1.111 molar solution. Another type of example, this one we want to know how many grams of calcium chloride do we need to make 750.00 milliliters of a .800 molar solution. So in this problem, we're actually given the molarity. Oop, I meant to be a highlighter. I do that way too often. We're actually given the molarity, and we're asked to use that to solve for the number of grams in my solution. So a problem like this, often where students kind of get stuck is where to start, right? I'm given two numbers as part of my problem, and then I'm asked to solve for grams. So like, where do we start? Like, what do these things mean? I just always remember that if you're given molarity as part of the problem, it's going to be my conversion factor, right? I'm going to write this out, and this is going to be true anytime I'm given molarity as part of the problem, unless I'm doing a dilution problem, which we will do in this chapter. I'm going to write this out. So I know that 0.800 capital M is the same thing as 0.800 moles of solute, right? For every liter of solution. That's what that number means. And remember I said anytime you have units where there's something over something, I can use it to convert between those two somethings. So I'm going to use that number as my conversion factor between moles and liters. That's what that number is going to be. So this is my conversion factor. Between moles of solute and liters of solution. So again, anytime you're given molarity as part of the problem, with dilution problems, you don't have to do this. You can, but you don't have to. But if it's not a dilution problem, anytime you're given molarity as part of the problem, I would write it out. Instead of keeping it as a capital M, I'm going to write it as moles over liters. It's not really obvious if you need to multiply by that number or divide by that number if you just keep it as a capital M. Remember, we want units to cancel, and we're not going to know if they're going to cancel if I just leave it as the capital M. So please write that out. And then that's going to be our conversion factor, which means I'm going to start with the 750 milliliters. Remember, we never start with our conversion factors. So essentially the question is, how many grams of calcium chloride do I need to make 750.00 milliliters of solution? And then the concentration of that solution is 0.800 molar, is how I would think about it. So I'm going to start with that volume. It is the conversion between moles and liters, not moles and milliliters. So we do need to convert that milliliters to liters first. And I'm just going to move the decimal place over. If you want to set it up, remember that there's 10 to the third milliliters in 1 liter. I'm just hoping that you're starting to become comfortable enough with the metric system that you can just move that over. So I'm actually going to just start with 0.75000 liters. Again, do not lose significant digits. 1,000 milliliters in 1 liter is an exact number. So 750.00 is 5 significant digits. That decimal point makes all those zeros count. So I need 5 when I convert it to liters. So 0.75000 liters. I now need to make liters go away. So I'm going to put the 0.800 moles on top because I want liters on the bottom. And then if we go back up to our problem, it wants grams, not moles, right? Right now, if I was to cancel these units, right, my liters are going to cancel and I have moles. I want grams, so we need the molar mass. So going back up, it's calcium chloride. So grabbing my periodic table, I want 1 calcium and 2 chlorine. So 40.08. Again, you can round to 2 digits after the decimal point, but don't do less than that. And then 2 chlorines. And I get my molar mass to be 110.98 grams per mole. Since moles are on top, I want moles on the bottom. So we're going to multiply by my molar mass. And my moles go away. And we're left with grams. So working this out, I'm just typing into my calculator right now. I got 66.6 grams of calcium chloride. 3 significant digits. So this has 5, this has 3, this has 5. So 3 is the smaller of those, so I want 3 in my answer. So it came out to 66.588, and then that 8 rounds the 5 up to a 6. So what this number means is if I was to go into lab and measure out 66.5 grams of calcium chloride and then add water until the total volume, you wouldn't add 750 milliliters because then you would have too much, right? We want the total volume to be 750 milliliters. Then the concentration of that solution is going to be 0.800 molar. And this is honestly, if you were working in a lab setting, the more common type of calculation you're going to do. So if we were in lab and the solutions are made up for us, we were to go do an experiment, and sitting over where they keep all the solutions, there'd be a bottle that had, of 0.800 molar calcium chloride. Well, somebody made that up. We have people that work in the stockroom, and they do this calculation during a typical semester, several times a day, prepping chemicals for us. So this is a very common, if you're ever working in a lab situation, calculation that you're going to be doing. One more example like this, and then we'll talk about some dilution problems, probably in our next video, actually. So let's say how many So another example for us. So what is the volume in milliliters of a solution prepared by dissolving, let's do 500.24 grams of glucose, which is C6H12O6, in water, so that the molarity is 1.546 molar. So what is the volume in milliliters of the solution? So this time we're solving for volume of our solution. And we're taking 500.24 grams of my solute, which happens to be glucose, and the molarity of my solution is 1.546 molar. I had said that anytime we're given molarity as part of the problem, unless it's a dilution problem, which we will do, I promise, I would write these out. So this is moles of glucose for every 1 liter of solution, right? That's what that number tells me. We're given grams of glucose. My molarity is moles of glucose. Remember, this is just my conversion factor. This is my conversion factor. We're never going to start with the conversion factor. So I'm going to start with that 500.24 grams. I am going to have to convert it to moles because, again, that molarity is moles per liter, not grams per liter. Then I can use that molarity as a conversion factor. So starting out, 500.24 grams of glucose. We do need the molar mass, right? Every time we convert between grams and moles, we're always going to use the molar mass. So again, grabbing the periodic table in my calculator, I have 6 carbons, I have 12 hydrogen, and I have 6 oxygen. And I get 180.18 grams per mole. Again, I am doing this pretty quickly, so please just press pause if you need to, and then figure it out, on your own. If I say, okay, I'm going to calculate the molar mass, and you're feeling a little rusty or you don't quite have it yet, it would be great to just pause the video, calculate the molar mass of glucose yourself, and then hit play again and see if you get the same thing I do. It's a great way to check your work and confirm that you are doing it correctly. So grams are on the top, right? Grams are right here. So grams are going to have to go on the bottom to cancel. So I'm going to divide by my molar mass. And those units then cancel. I now have moles on the top. So my molarity is going to have to go on the bottom. So 1.546 moles of glucose for every 1 liter of my solution. And then I cancel those out, and I end up with liters. And then we can just move our decimal place over to convert it back to milliliters. And this is one of the places where if you don't write this out, if you keep it as a capital M, it's not obvious, at least to me it's not obvious that you have to divide. As soon as you have that M there, as soon as you have moles there, and you see this moles on the top, then you know you have to divide by your molarity to get those moles to cancel. So I'm typing this into my calculator again. Oop, I typed in 0.25, not 0.24. I miss having you guys in class to check my work. And I got 1.7, we want 4 sig figs, 96 liters of solution. Oh, SOL. This SOL with an apostrophe N is my abbreviation for solution. So if we go back and look at the problem, it does ask for milliliters, so I do need to convert that to milliliters. The easiest way to do this one, because it's already 1 point something, is to just throw 10 to the third at the end of it, right? Remember, 1 liter is equal to 10 to the third milliliters, and then proper scientific notation is always 1 digit, then the decimal point. So since it's already 1 digit in the decimal point, I can just throw times 10 to the third on the end of it, and it's a really quick conversion. If that doesn't make sense, by all means, work it out using dimensional analysis, but this is the answer you're going to get. Significant digits. This is 5. These zeros count because they're between non-zero digits. This is also 5, right? This 0 counts. And then this one is 4. So I wanted 4 in my answer. This is exact, so I still just want 4 in my answer.